in atoms, example 21. The energy level diagram is given. Okay, so they've given one diagram here. This energy level 0.85 minus 0.85 electron volt. This is minus 1.5 electron volt, minus 3.4 electron volt, and there's the minus 13.6 electron volt. They give you like this, you can copy this readings for the energy level diagram. You don't have to sit and memorize it, but you are not sure whether they will give you or not, so you better memorize it. They're given this diagram where this is jumping from something that's jumping like this. This is A. There's something which is jumping from here to here, which is B. Something jumping from here to here, C. Something that jumps from here to here, which is D. Okay. So then they're saying energy level diagram of these elements have been given. Identify by doing necessary calculation which transaction corresponds to emission of spectral lines of wavelength. Some wavelength has been given 102.7 nanometer. When they give you wavelength, no, what you do is immediately calculate the energy. You know E is equal to H mu. So E is equal to H mu means E is equal to H into C by lambda. So this lambda, you can find the energy because lambda has been given. Planck's constant is something that you know, which is what is Planck's constant? 8.8 into 10 to the power minus 34. Where is Planck's constant given here? 6.6 into the power minus 34. I'm sorry. So remember Planck's constant, it will be given in your question paper. 6.6 into 10 to the power minus 34 into C itself is 3 into 10 to the power 8. 10 to the power 8 by lambda is 102.7 into 10 to the power minus 9. When they give you a particular wavelength, quickly calculate its energy because Hc by lambda, everything else is a constant. You can get the energy's value. The energy's value will be, you will get an energy here, which is H 6.6 10 to the power minus 34. C, meters, lambda meters. So you will get in joules. But you need an electron volt because this variation is in electron volt. To convert the joules answer into electron volt, you have to divide it by 1. This answer has to be divided by, this energy that you get has to be divided by 1.6 into 10 to the power minus 19. Then you will get the answer in electron volt, which happens to be 12.1 electron volt. Are you clear? You have to do this and keep it aside. Now you have to see which one corresponds to, if you subtract, which one gives you 12.1. The energy level gap, which one gives you a 12.1, the difference in energy level, right? So then it will be like, what will be the difference in this? Difference will become, it will become subtraction. Because minus 1.5, minus of minus 0.85, correct? Yeah. Become minus 1.5 plus 0.85. So minus 1.5 and a 0.85 will be, this is 0 means 5, this will be 15 means it will be 7, 0.75. It doesn't correspond to this. So the first one is not there, correct? Let's go to B. What is B's value? Okay, what is B? B is jumping from there to here, which is 3.4 minus 0.85. Now that you know subtraction, generally subtract and see. This is 5, this will be 3, this will be 13, this will be 5, this will be 2.55 is the gap, is it? So then therefore, since this is 12.1, it cannot be any of this. You can guess that. It has got to be something to do with this D. That's where the huge value lies, correct? So can we do D, which is what is 13.6 minus? 13.6 minus 1.5 will be 12.1. So you can guess that and then, so the time can be saved. Are you clear? So then therefore only D corresponds to this wavelength. So that's this question. So let's go to, what is D? Okay, well, what is D actually? It comes to the first octet, ground state. From n is equal to, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3. From 3 to 1, anything that falls into 1 will be Lyman series. So this is one of the Lyman series, correct? So then they will ask you to identify what series it is, Lyman, okay? So let's go to next question. It's the 22nd question. The energy of the electron in the hydrogen atom is known to be expressed as En is equal to minus 13.6 electron volt by n square, where n is equal to 1, 2, 3. We all know this, correct? The electron in the hydrogen atom cannot have an energy. Use this expression to show that the electron in a hydrogen atom cannot have an energy which is minus 6.8 electron volt varave varadhu justify pannum. If you put E as minus 6 you won't get n's value. You have to get a proper n's value. It cannot be a fraction, right? Correct? Yeah. So if you have minus 6.8 electron volt energy irundadna, it will be minus 13.6 by n square. So n square will be 13.6 by 6.8. Is 6.8 into 2 is what? 8 to 16, so 13.6. You're getting n is equal to 2, right? Root 2 nu varudhu. N square is root 2. N is equal to root 2 nalla unakku varakudadilla. Octet cannot be root 2. Yeah, what did I do? If I took the energy to be minus 6.8 to justify that, it cannot come. That should be equal to minus 13.6 by n square. So I'm trying to find what is n square. If n square is 4, then it will be 2. But n square itself cannot be 2. So n cannot be root 2. So such a thing is not possible. That's how I would justify. I won't justify it like him. He is writing energy level of the first orbit minus 13.6 electron volt. Energy level of 2 is what? Minus, what is it? 3.5 electron, 4 electron volt. E3 is minus 1.5 electron volt. Next E4 is minus 0.8 electron volt. Next is, so then there's no 6.8 there. So he's saying there's no 6.8. So you can do it any way you want, whatever way you want. So clearly an electron, the hydrogen atom cannot exist in this. I am doing it differently, okay? So let's go to next second subdivision question. The spacing between the lines with within the given set of observed spectral lengths decreases as n increases. Spacing between the lines. The spacing between the lines is nothing but the energy gap. Is it's minus 13.6. Then it's minus, again I'm coming back to you. What is it? Minus 3.4. Then minus, can you see as the gap decreases, as the energy gap decreases, this is also decreasing, correct? So then as the spacing between the lines, that is energy levels, decreases as n increases. Yeah, correct. It decreases as n increases. You all know from this itself explains it, correct? So then that itself explains it. As the value of n increases, the energy difference between the two consecutive energies, because energy itself is minus 13.6 by n square. As n increases, E will decrease. That justifies this. Can I go to next question? So example 23rd. So they have already given this drawing, which is n is equal to 4. There is an n is equal to 3. There is an n is equal to 2. And an n is equal to 1. 1. Who can, octet cannot be minus 1. So they given this diagrams where it is like this, where this is like this, where this is like this. The 3 lines are there. Then this is like this is like this, and this is like this. Some diagram like this has been given. So find out the transition. Okay, find out the transition which results in an emission of photon of wavelength 496 nanometer. Every time they'll give you wavelength. E is equal to h mu. E is equal to h into c by lambda. H is what? 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8 by lambda itself 496 into 10 to the power minus 9 nanometer. This has to be divided by 1.6 into 10 to the power minus 19 to get the electron volt answer. That electron volt answer itself is, let me tell you, is 2.5 electron volt. You get it like this. Now you subtract and see which one is going to have they given the, they have not specified the energy, but you know the energy level. Yeah. You know it's minus 13.6. You know this is again 3.4 electron volt. This is minus 1.5 electron. This is minus 0.8 electron volt. Yeah, and so on. And so then, so you can see which one will get you 2.5 electron volt. Definitely you can't subtract this and this. You will never get 2.5. So you can ignore this, because this is a graph between this. So only thing is we have to stick to only other things. 3.4. So it cannot be any of the 3. None of, no, any of the 2. First and second one. Yeah, the other things are possible. So let's subtract 3.4 with 1.5. This will be 14, be 9, 2, 1.9. It's 2.5. Okay, finished. Yeah? This cannot be, not possible. This is possible, which is 3.4 minus 0.8. This is 14. 8 means this will be 6 and this will be 2. 2.6. You closer to it, correct? Which one is coming closer? Let me do it. And this one is 2.6 electron volt. Let's do the last one, which is 1.5 and 0.8. This will be 15. It cannot be. You're going to subtract. Cannot be. So the only thing which is closest is this. And I don't know what am I supposed to write. It's E4 minus E2. It's E4 minus E2 is appearing to be closest. We can't exactly arrive at it. So that's all. That's all. So 4 to 2. It's jumping into 2, which means like Balmer series. You're able to identify the series, you're able to do the sum. Can I go to the next one?
Yes, ma'am.
Then they're asking you for, sometimes I'll tell you what they'll do. They'll ask you to identify which spectral line, whether this is gamma rays or, I've taught you the tabular column in which I've told you to memorize the wavelength and frequency. Were you there when I took electromagnetic waves? But it's there in the recording. Please, I cannot go on like this. So then you have to look at the way. I'll teach you if you want only the tabular column part. Finish the portions and come. Come and explain to them the whole lesson. If you do that, then I'll teach you. Okay, if you take 2 steps, I'll take 1 step for you. If you finish the entire lesson, I'll tell you how to remember the frequency and wavelength. As soon as you go into the exam hall, you can tabulate it immediately in some rough paper. Story thing, watching radio, TV, watching Maniratnam movie and all that. So with that clue, you can memorize that. And then this wavelength will correspond to which wavelength in that tabular column. They might interlate this with electromagnetic waves, for which you should know the tabular column. I'll help you to memorize the tabular column again. We'll do it even in the class. Everybody has to recap. You can do it in the class. I hope people are coming and are not stopping. So then let's go to 24th question. Use Rydberg formula. Rydberg formula means R into 1 by n, enga vandu with 2. To where it's fallen from ni square. N final square minus 1 ni square. Which is 1.09 into 10 to the power 7 per meter is the Rydberg. They would give you the Rydberg formula. Okay. So then you won't have a form, you don't have to mug it up, I think. So then this will give you 1 by lambda only. Using this formula, whatever you find is only lambda. After you find lambda, you can find energy. Because E is equal to h mu h into C by lambda. You get 1 by lambda itself here. You can directly put 1 by lambda itself in here and multiply so that you get the energy. You can h into C into 1 by lambda. If they ask you about the energy. Okay. So using Rydberg formula, calculate the wavelength. Means you have to do 1 by lambda. This formula only you have to do. The Lyman series. First 4 spectral lines of Lyman series. So n is equal to 2 to 1, 3 to 1, 4 to 1 and 5 to 1. Correct? Can you see? So, so you have to do 1 by lambda is equal to R into 1 by Lyman series, right? 1 square minus 1 by 2 square. Then 1 by lambda is equal to R into 1 by 1 square minus 1 by 3 square. 1 by lambda is equal to R into 1 by 1 square minus 1 by 4 square. Like this you should go on, right? What they are doing is, yeah, you also find like that now. What is there? Because you can quickly do this. Okay, 1 by lambda is equal to R is 1.09 into 10 to the power 7. 1 by 1 minus 1 by 4, which is nothing but 4 minus 1, which is 3 by 4. So 1 by lambda is equal to 1.09 into 10 to the power 7 into 3 by 4. So you can find what is, you need only 1 by lambda if you're going to find energy, but they're not asking energy. Asking you for the specific wavelength. You have to reciprocal this. Won't you get into a problem reciprocaling this? Yeah, you will have a problem. Yeah. That's why what they're doing is, they are trying to find an LCM for this formula and arrive at a new formula for wavelength itself. So that final reciprocal thingy will not be there. So what is it, 1 by lambda is equal to R into 1 by n final square minus 1 by n initial square, correct? So then R is equal to 1 by 1 square minus 1 by, this is going to be always 1 square, this is only going to change, correct? So then it's 1 by lambda means, if you take LCM here, what will be the LCM? Ni square will be LCM. It will be Ni square minus 1 only, correct? So lambda therefore is Ni square by R into Ni square minus 1. So then you can directly calculate the Ni square is 1 in every case. By Rydberg constant is 1.09 10 to the power 7 in every case. Yeah? If you can find this answer and keep it, you can just multiply with Ni square, which is Ni square minus 1. So it's going to jump, no, it's going to jump into 1. So there should be a final square. N final square, where is it? N final is 1, Ni square, okay. So this Ni square minus 1, Ni square. So where it's jumping from, this is not 1, this is where it is jumping from. So it can jump from 2. So it's be 4 minus 1. It's also 4, ni
yes,
square. Yeah,
ma'am.
4 by 4 minus 1. If it's going to jump from third, it will be 9 by 1.09 10 to the power 7 by
9 minus
8. There are 9 times, so 3 is 9 minus 1, 8. So like this, you can just write this. Correct? And you can calculate. That's way they have done it. Okay, so they have found each and every wavelength. Okay, can I go to next sum? Is example 20, example 26. Okay, calculate the shortest wavelength. Very, very important question. When they say shortest wavelength, it is means shortest wavelength means highest frequency. Shortest wavelength means highest frequency. When they say highest frequency, the energy gap has to be maximum. Energy gap will be maximum only when it falls from infinity to that octet. From infinity to that, the highest energy of a Lyman is n is equal to 1 from infinity. The shortest wavelength means highest frequency. The highest frequency means energy E is equal to h mu has to be maximum. Energy gap is maximum. It has to fall from infinity to that octet. Are you clear? So then, there's the question here. Calculate the shortest wavelength of the Lyman series. So n is equal to 1. It has to jump from infinity. And you know the formula is r into 1 by 1 square minus 1 by infinity square. 1 by infinity is anyway 0. R itself is 1.09 10 to the power 7 by 1. That will give me 1 by lambda. Therefore, lambda is a reciprocal of this. 1 by 1.09 into 10 to the power 7. Okay. Whatever the value is, you will get in Armstrong 10 to the power minus 7 amela pohom dila pohom. So you'll get the wavelength, and that's all. That's all. That is the shortest. That is the shortest wavelength because highest frequency. Whatever you calculate itself is the. Are you clear? The understanding of the question. Sometimes they'll ask you longest wavelength means shortest frequency, which means it should jump from the immediate orbital. So from n is equal to 2 to n is equal to 1 it should jump. Those are called H alpha line. I have to teach you that. H alpha line means when they give you H alpha, it means something is jumping from second to the first octet. That means H alpha line. Okay. So then I'll see if I'm able to trace out any sums to the H alpha. Otherwise we have to see the net. Board exam has got H alpha lines. So can I go to next question?
Yes.
Do you understood the shortest wavelength and longest wavelength? Next question also shortest wavelength. I'm not doing it. Okay. But it is in the Balmer series, which means it's going to jump into 2 from infinity. 1 by 2 square minus 1 by infinity. Correct? I don't have to do it. So can I go to example 28? Using Rydberg constant, find the longest wavelength. I don't have to do it. I just taught you longest wavelength means shortest frequency, which means you should jump from the immediate orbital of a Lyman series means going to jump from second to the first. You can see it for yourself. That's a sum which is 28 sum in Aurora. So then the 29th question. H alpha line. I was looking for an H alpha line. Came for a CBSE paper. H alpha line always stands for, okay, first of all I should say one thing. The H alpha line is not for a Lyman series. It refers to only for a Balmer series. H alpha line is a line that's given only to Balmer series, which means jumping from third to the second. When it jumps from the third to the second, that's when you get a H alpha line. They're asking for the wavelength of it or the frequency of it. You know, 1 by lambda is equal to R into 1 by 2 square minus 1 by 3 square, and R itself is 1.09 10 to the power 7 per meter. So if this you reciprocal and you get your value of lambda, and then they ask you frequency, you know, you get lambda, you know, C is equal to, mu is equal to C by lambda. Velocity is distance by time. Velocity is itself C, distance itself is wavelength, 1 by T itself frequency, so mu is equal to C by lambda. So with that, you know, C is 3 in 10 to the power 8, lambda is something you would have found out, you can find what is mu. Are you guys clear? So very, very important sums. Everything is very important in this lesson. And H alpha line refers to Balmer series. Whenever they'll only ask you H alpha, they'll not ask you anything else, nothing else in the portion. It refers to Balmer series, so you can't think it is Lyman. For a minute I said it's Lyman, it's not. Lyman series is called some H ly something. It's not H alpha. H alpha refers to Balmer series only. Can I go to next question? So again there is another one, the wavelength of a H alpha line in Balmer series. They have H alpha in Balmer series has been given, but if they don't give, you should know. The wavelength has been given to be 6563 Armstrong. Calculate the Rydberg constant, that R. You know it has to be 1.09 10 to the power 7 per meter, you have to derive that. This itself is 1 by lambda. It's 1 by 6563 into 10 to the power minus 10. Itself is R, which is 1.09 into 10 to the power 7 into 1 by its Balmer series 2 square minus 1 by alpha line, right?
3 square.
3 square. So you can cross. This is R. You have to calculate this R. That's the question. The unusual. Why would they? That's a constant. Why would they ask you to do that? In case they do that, you can tell. Okay. Example 31. The short wavelength limit for a Lyman series. Shortest wavelength means highest frequency coming from infinity. And that's for Lyman series. So it's infinity to 1. And 1 by lambda is equal to R into 1 by 1 square minus 1 by infinity the whole square, which is infinity 0. This 1 by lambda itself is R, therefore is 1.09 into 10 to the power 7. So lambda itself is reciprocal of it, correct? But the question doesn't stop there. Okay, the shortest wavelength of a Lyman series itself has been given. Calculate the shortest wavelength limit for a Balmer series. Okay, so using this I have to do something. Using this I have to do something. Okay, so then I know this itself has been given. What is it? 1 by lambda itself is for a 913.4 into 10 to the power minus 10 is equal to R by 12. This is the shortest wavelength has been given. So R by 1 square, which is R by 1. This is for a Lyman series. Using this I have to find the shortest wavelength of the Balmer series. You all know that the wavelength is always 1 by 2 square. Just the 4 will be there. You already know R's value can be plugged in from this. So put that and then reciprocal it. What else can we do? Correct? But they are saying correct only. Yeah, reciprocal it. Okay, forget it. Okay, so can I go to next? Okay, this sum is interesting. Example 32. Find the wavelength of the electron orbiting the first. Okay. Find the wavelength of the electron orbiting in the first excited state of the head. N is equal to, first excited means N is equal to 2. First excited state doesn't mean N is equal to 1. N is equal to 1 stands for. So N is equal to 2, you have to find the wavelength. If you have to find the wavelength, you can find the energy. Energy of the second octet itself is what? Energy itself is minus 13.6 by n square, which is minus 3.4 electron volt. And you have to find the wavelength in it. H into C by lambda is equal to minus 3.4 electron volt, correct? So then what is 1 by lambda from this is minus 3.4 electron volt by H into C. Is that what he has done? He has not done that. Okay, 1 second. He has not done that. Okay, let's see. The question is to find the wavelength. Okay, he is using de Broglie's hypothesis. Okay, that's another way of doing. It's a beautiful way. De Broglie's hypothesis, according to which, the entire perimeter of the atoms consists of electrons, which is revolving, accelerating, which is emitting wave. And is n lambda, which is 2 pi r is equal to n lambda. Yeah? 2 pi r is equal to n lambda. Therefore, here n is equal to 2. So it's 2 pi r is equal to 2 lambda. You want to find lambda, it's 2 and 2 get cancelled, pi r simply, correct? But you should know what is the r of the second orbit, and you have mugged up what is the formula to find the radius. R is proportional to n square. R is equal to r naught into n square, where r is equal to some Armstrong, what was it? 0.53 Armstrong into n square. 0.53. Yeah? Okay, okay, 1 second, I'll just quickly recap that. It will come here. No, it's before 1 by C. This is atoms lesson, right? Yeah, I think I'm skipping a page. Here, C by N. 0.53. Confident, good, excellent. So then that's 0.53 Armstrong into n square. So r is equal to 0.53 into n square itself is 4 here, with which you can find an r into 10 to the power minus 10, of course. Okay, and then take it and substitute it here. Hence, you can directly get multiply with 3.14. You can get the, instead of doing the energy part, this is so easy. where we are using de Broglie's hypothesis to find the wavelength of any electron using, if you know the radius. This is one question which we can challenge to others. Okay, by way of challenging, you will also be able to recall, and they'll also be able to just remember this. Okay, so the next question is okay, that's done. This is example 33. Example 33, a 12.5 electron volt beam is used to excite a gaseous hydrogen atom at room temperature. Determine the wavelength and the corresponding series of the lines emitted. Okay, a 12.5 electron volt. Okay, you know what will all give you 12.5 electron volt? You know, minus 13.6 is this. And this will be minus no, she has to say. It's not 1.5. Minus 3.4. Then it's 1.5. What all gaps will be sufficient for 12.5? Even this will be sufficient for... No, it won't be. 13.6 minus 3.4 it is it? Yeah. The 12.5 electron volt of energy that's falling on this is capable of doing this. Will it be capable of doing this? Yeah, everything will be... no, the gap is narrowing. 13.6 into 1 minus 1.5 is 11.1. That's 12.5. Sufficient. Maybe when it comes to 0.8, 13.6 minus 0.8 is 8. 12.8. What is it? No. So whatever, it's n is equal to 1, n is equal to 2, n is equal to 3. All these transitions is possible. What about 3 to 1? What about 3 to 1? 13.6, 1.5 also are done. Okay, yeah, so it can fall from 3 to 2 or can fall from 3 to 1, it can fall from 2 to 1. This is my inference. So 3 to 2, 2 to 1, 3 to 1, that's all. These are the energy levels, gaps which are matching with the incident energies, or its incident energy is greater than all these gaps. Therefore, all this is possible. If the incident energy is less than these gaps, it cannot excite it. Correct? Are you clear? So then they are asking you to find the wavelength. You know that it's respectively lambda 3.1, lambda 3.2 and lambda 2.1. Correct? Yes. And the lambda's formula is R into, okay, lambda itself is, oh, in this they are not using R into 1 by n1 square. Okay, you don't have to do that here. You know, E is equal to H mu. E is equal to H into C by lambda. So lambda itself is Hc by E. So if you know Hc, constants, by the energy level, that lambda 3.1's energy gap, 3 to 1, what is the energy gap? That gap, that subtraction is 3 to 1, which is 13.6 and 1.5 is 11.1. But he didn't put 11.1 anywhere. This is 12.1. It's 12.1. Okay, so then make sure you subtract. That gap has to be, delta E has to here. You should remember that there can be this formula also, which is very simple because you know the energy. Why to use R and reciprocal and all that? So easiest thing when it comes to this is to do Hc by delta E. Just mug up this lambda is equal to Hc by delta E. If you know that, every wavelength can easily be calculated. Are you clear? I'm not doing this sum. I hope you can learn it from Aurora. Yeah. So let's go to next question. I won't deal with this question, Hamsini, where it's n into n minus 1 by 2. What are the possible energy drops? Okay, I'll just form my own question. Okay, so I think it's enough. Whatever I've done is enough for you. Okay, and okay, so CRT question. Okay, I'll do it. I'll do a few more. Example 34. Remember, remind me to do that question. It's n into n into n minus 1, n plus 1. I'm not sure that question we have to dig out from the internet and do it. Example 34. We're going to finish it. Lesson is going to be over. A 12.9 electron volt beam is used to bombard a gaseous system. That is the incident energy. So energy gap has to be always lesser than this, and then it's possible to excite it. Correct? So it seems it's from 4 to 1 it's possible. 4 to 3 is possible. 3 to 2. Okay. The question is about up to which energy level the hydrogen atom would be excited. Okay. See, I'm bombarding the hydrogen atom with this much energy. The electron will jump from n is equal to 1 to whatever orbit. Here it's not falling, it's absorbing the energy and jumping. So it can jump from n is equal to 1, it's minus 13.6, to jump to n is equal to 2. Whose gap is minus 3.4. I don't know, I have a mental block there. What is the gap between these two? It's 12.1, 12.2 or something we saw, no? 13.6 and 3.4 is 10.2. 10.2. 10.2, is it enough? What was the incident energy? 12.9, yes. So it can jump to the first octet. It can even jump to, it can actually has sufficient energy to jump to the third octet, which is minus 1.5 electron volt. The gap itself is, here is where it's 12.1. Here is where it's 12.1. If you can mug up the gaps, it will be good. 10.2 and 12.1. 12.1, 12.9. Yes, it can jump into 2. Can it jump into 3? 0 minus 0.8 electron volt, which is 13.6 to 0.8. 16 means this will be 8 and this will be 12.8. Yeah, it can. So it's that's all it's possible. So it can jump from here to here. These are the various diagrams which is also written beautifully. Correct? And you know they asking you to calculate the wavelength. We have a simpler way to do the wavelength. Wavelength is equal to hc by delta E. You know the energy caps, you can substitute and calculate the corresponding wavelength. That's not what he has done though. But we can do it like this because we are amazing. We just learned it and we are able to apply it here. So let's go to example 35. Okay, example 35. Which state of the triply ionized beryllium ion, 3 plus ion, has the same orbital radius as that of the ground state of hydrogen? Okay, which state of the beryllium has the same orbital radius as that of the ground state of hydrogen? Triply ionized beryllium has the hydrogen, helium, lithium, beryllium. Beryllium has got 4 electrons. It lost 3 electrons, so it's got only 1 electron now, which is similar to that of the hydrogen, but it's an ion. It's got 1 electron. Which state of triply ionism has the same orbital radius as that of the ground state? It's the same orbital radius. Okay, you remember I told you R is equal to R naught into N square. That is for a hydrogen atom. If it's for any other atom, it will be R naught by Z, because R itself is N square H square by 4 pi square M K Z E square. We are taking for a hydrogen atom, so we consider Z to be 1. If it's anything other than hydrogen, it has to be Z. So then therefore it has to be N square R. So this is the formula. Therefore, you should also know for any other atom, R will be proportional to N square by Z. So, R is proportional to N square by Z. And this is for radius of the, radius of the beryllium has to be equal to the radius of the hydrogen of the first octet. Okay, nth octet. Some radius has to be equal. I don't know. Nth octet is N square by Z. Radius of the nth octet of beryllium will be N square by Z. Radius of the first octet of hydrogen will be 1 by Z is just 1. So N square has to be Z. So N has to be root of Z. What is the atomic number for beryllium is 4. So N is equal to 2. So then thus N is equal to 2. Thus it will have the N is equal to 2 will have the same radius as that of the hydrogen. I really don't understand the question, but you understood what I am doing in the sum. Okay, similarly we have one more NCERT sum, which is example 36. Which level of doubly ionized lithium? Similar question. Lithium, hydrogen, helium, lithium is third element, 3, it's 2 plus, which means it's lost 2 electrons, behaves like an hydrogen atom. 1 electron only is there. Has the same energy as the ground state of the hydrogen atom. The ground state of an hydrogen atom, you know, has got energy minus 13.6 by 1. Minus 13.6. So you write here, energy of a lithium, 2 plus, has to be equal to energy of the first octet of hydrogen. Correct? And energy of the first, energy is directly proportional to, okay, do you remember energy's formula? Energy is minus k Z square by 2r, where in the place of r I'll substitute n square h square 4 pi square m k Z square, and where 2 and 2, 4 got cancelled, I'll get a formula. Therefore from this you know is inversely proportional to n square. Can you see? And it's directly proportional to z as z square. Z square. So therefore, you know, energy is directly proportional to z square and inversely proportional to n square. So this is something again I want you to memorize. So then therefore, it is z square of the lithium by n square of the lithium is equal to z square of the hydrogen by n square of the hydrogen. What is the atomic number of lithium is 3. So it's 9 by n square is equal to hydrogen. What is the atomic number? Is just 1 by 1 square. So n square is equal to 9, n is equal to 3. So that will have the same energy as this. Some question like this comes, this is what you're going to do. And you should know the relationship. What is the moral of the story? You know the moral of story is R is proportional to n square. R is equal to R naught into n square. All that is fine. But that's only if it's for a hydrogen. Generally it's n square by Z. Similarly, energy will be proportional to n square by Z square. Z square by n square. Absolutely right. These are things you should know. And velocity, you know, is 1 by 137 into c by n, where n is equal to 1. It goes like that. That I know, but they're not asking about any velocity sum yet, so we can ignore it. Okay, so then that's about it. Are you clear with these sums? I want to just check on only one sum, where how many number of possible spectral lines can come when it falls from. I am just trying to look for a sum. Energy level of atom, which of them will result in transition of photons of. See, there's the sum where they're talking about, there's a problem number 11 from behind, where they're talking about a photon of wavelength 275 nanometer. Immediately you calculate the energy, calculate the gaps, and you know it. I don't have to say it. I thought it's a different sum.